In this video, we're going to talk about defining velocity vectors of a curve on a manifold. Let us start by looking at how we define velocity vectors of a curve in calculus. Let us bring in our coordinate system with a plot and place a point on the plot. Now we can define an arrow from the origin of the coordinate system to that point with components 1, 1. If we move along the curve, we get the following behavior. Let us move back to the initial position. The curve has the following parameterization. If we take the derivative of this parameterization, we get 1, 2x, which is the components of our velocity vector. We can bring in our velocity vector and move along the curve. We want to define the same velocity vectors on a curve on a manifold. Let us place an arbitrary manifold. On this manifold, we have some smooth curve gamma, which can be viewed as a function from R to M. We can try taking the derivative of this function. The derivative has the following definition. So let us pick 2 points on the curve. We have a problem. On an arbitrary manifold, there is no notion of addition between 2 points, so we cannot do this. Mathematicians use a trick. They make a set called C infinity of M, whose elements are functions that map from M to R and are smooth. So let's place gamma R to M on the left side and pick some arbitrary smooth function f M to R on the right side. If we start with a rail line on the left side, gamma will take this line and map it to the following curve on the manifold. Then the arbitrary smooth function will take the curve and map it to a rail line. We get the following function f after gamma, which we can take the derivative of because addition is defined on real numbers. So there we have it. We have defined derivatives on a manifold, which means we can construct the velocity vectors of a curve on a manifold. Now you might be thinking, this does not mean anything because f is arbitrary, and you would be right. To make sense of this definition, we need to use charts. Before we go there, I would like to go off on a tangent about tangent spaces. We define a tangent space at a point P on the manifold as the following set, where nu gamma p is the tangent vector of gamma at P. Let us pick a point P on the manifold and draw different curves. We can then draw the tangent vector at P for each of these curves. All of those tangent vectors belong to the set TPM. The tangent vector nu gamma p of f is defined by its action on an arbitrary smooth function as equal to the derivative of f after gamma at some point lambda 0. To compute the components of these vectors, we use charts. If we take an arbitrary chart, we can do the following. From now onwards, I will write derivatives in the following notation. To get the components of a velocity vector, we pick an arbitrary chart x and insert it into the derivative. We can do this because x inverse after x is always equal to 1. Then we can make the following groupings because function composition is associative. After that, we apply the derivative with the chain rule, which gives us the following. Here we are using Einstein's summation notation. Next, we just change the position of the two terms. Finally, we make the following definition. The only change is on the right term. All this is saying is that the right term in the last line is defined to be the right term in the second last line. Since f is arbitrary, we can replace it by an underscore. So given a chart x, the following is true for any arbitrary smooth function f. At this point, we have defined how to take derivatives of a curve on a manifold and can use this equation to get the components of our velocity vectors. Let us make this concrete by studying an example. Let us look at the example of a circle. If we recollect, a circle is just a set of tuples. If I go around the circle, we see the different values these tuples have. Before we compute the velocity vector on this circle, we need to derive charts. In my previous video on manifolds, I used the circle as an example and made 4 charts. In this video, I would like to derive another set of charts. We start by drawing a line from point 1, 0 to an arbitrary point xy. The slope s1 of this line has form s1 equals y over x minus 1. The line above represents the chart, and the point on the circle corresponds to the point on the chart. We can move the point xy around and compute the slope for the line. Notice as we approach point 1, 0, the slope explodes. If we use the slope as a chart, the only point we cannot describe on a circle is 1, 0. The solution to this issue is to compute the slope for a second line. Let us go back to our original point. We can then draw a second line from point -1 to the arbitrary point xy. The equation of the slope for this line is s2 equals y over x plus 1. The second chart goes to infinity as we approach point -1, 0. We can rename these charts to chi left and chi right, where left means we use it on the left side of the circle and right means we use it on the right side of the circle. We can also compute the inverses of these functions. They are the following. To derive these expressions, you need to use both the charts and the fact that we only use input points from a circle. Now that we have defined charts for a circle, let us do some algebra. We start by defining our curve to be gamma of alpha equals cos alpha sine alpha. This curve just goes around the circle. Next, we apply the left chart onto this curve, which gives us. After that, we take the derivative of this expression, which gives us. Previously, we had derived the following expression for the derivative on a manifold, where underscore represented an arbitrary smooth function and x was an arbitrary chart. If we use our left chart, we get the following. We can then substitute the derivative to get the following. Let us try to understand what this means. The -1 over cos alpha minus 1 is just a scalar quantity. It depends on the choice of the curve gamma and chart. What about the term partial over partial chi L? This term is just depends on the chart. It is a basis vector. Let us try to understand what this equation is telling us. We start by bringing our chart. Then the basis vector at a point, say 0.79, is the following arrow. If we move along the chart, the arrow just stays the same size. This is our basis vector. We can then make it scale according to the scalar function we have. We get the following behavior. That is it. We have defined velocity vectors on a manifold by using charts and arbitrary smooth functions.